Hello class, I just wanted to introduce myself. My name is Bartholomew Lindberg, and I am going to do a brief presentation on this power conversion project for REE 413 at Oregon Tech. To start off, we were told to go to a website and pick up the toolbox. If we have the toolbox, we should be able to download this simulation for a 100 kilowatt grid connected PV array. And the reason I'm bringing you to the website first is because that's where we originally will see the description of everything, every component that's going into it, and there are a lot of different components that go into it. So first we have the PV array as the first bullet point, and the boost converter, our three-level, three-phase DC to AC converter, and then we have a capacitor bank, which filters out the harmonics produced by the VSC. And then we have a 100 kilovolt amp three-phase coupling transformer, which is going to step up our voltage to make it good enough for the grid. And here is our utility grid, which is the last part of this schematic. And then we can go, right now, I'm just going to go into the parameters of the PV array. And just so we don't have to go into that later when we go back to the schematic. So just keep in mind the number of cells, the open circuit voltage and the short circuit current are both given. We're given the maximum power point of each one, and this allows us to calculate for maximum power. So we can compare those with our own calculations. And when we're running the simulation, they give us the irradiance and the temperature at which the operation is going to be happening. And they talk about all these different measurements that they put on the scopes to help us understand what these scopes are and what they're doing. And that's very helpful because some of the scopes that they were using, the names weren't that useful to actually understand what's going on. And here you can see the maximum power point. They actually did it for us at 100.4 kilowatts is obtained with a duty cycle of 0.454, and as I was absorbing it, and I expected the duty cycle to be right around this area. And there's the rest of that. There's the references if you want to know more information on it. Let's go to the simulation file now and talk about a little bit about each component. We have the maximum power point tracker controller. We're going to be using an incremental conductance technique, and this is kind of a hybrid because whoever made this model has made an integral regulator within it which helps calculate the error, and it gives it like a PID control. So here is the inside of that maximum power point tracker. It's going to have all its flags going in, but what we're interested in is what's inside of this box. So here we're going to see two branches. The bottom branch has a feedback loop of the maximum power point tracker with a gain and the error message, which is what we need to calculate for in order to help get to maximum power point faster and more efficiently. And then this looks like the top part is going to be your main algorithm for that increment conductance. Sorry, it's not focusing very well. And then so that's that. Alright, I'll go back out to the main schematic now. And come back out. And let's get this video to zoom in some. Okay. Now the PV array, we've gone over those parameters. We can go over that more. If you have questions, just leave them comments in the YouTube channel below. Here's your boost converter. And as you can see, this boost converter. What the heck? Okay, I'm just going to keep going with it. I don't know why my screen is so fuzzy right now. Okay, now it's focusing a little better. Okay, here's the boost converter. You can see the main schematic. The gate signal is coming from the pulse, which is the maximum power point tracker. And then we have our inductance and everything. It's just a regular old boost converter, nothing too special about it. The connections are just a little bit slightly different because we are introducing a controlled input pulse for the gate signal. And then there's the PV, which is our input DC power for that boost converter. And then here we're going to go to our 3-level VC 500 volts, 3-phase DC to AC inverter. So let's go ahead and just make that bigger. See if that'll focus in some. There we go. The level 3 bridge is the DC to AC inversion, and that's going to bring us into 3 phases. Here are our 3 phases that are coming out. And then we're going to have a load resistance on each of that phase. And then once we get outside of that phase, we're going to have this power. Let's see if we can get this over to the side. And this power bank here, which is what we were talking about earlier in the descriptions. With the power bank, it says 10K VR, and that's capacitance. And I'm not quite sure all the reasoning was that is for, but we can go more into that later. Here is the transformer. It's going to step up the voltage from 260 to 25 kilovolts, which would make it useful for the grid. And then the last thing in our schematic is that utility grid right there. And you can see we've calculated our power, and we have our scopes for in kilowatts, which the volts is right below it. That's the grid volts and the grid current. So now let's go into those different oscilloscope readings for each of these, and hopefully get to answer some of these questions or some of your curiosities about this system. Alright, here is the PV scope, and it had several inputs for it. So there are going to be a couple of different measurements, but we have our temperature. You can see there's a spike later on at about time equals 2. And then our power mean at first is sinusoidal, and then it reaches a steady state, and then we have this drop in the middle of again. I'm not quite sure why that's going there, but then it does reach a steady state again later on. Here's the mean voltage, which is also going to have to reach a steady state as well, and you can see it's kind of tracking the power, and those are proportional to each other, so that makes sense. And then here's the duty cycle. You can see the changes that the maximum power point truckers had to make to ensure that the power is restored to maximum. Alright, and then we'll look at the VSC scope, which defines the absolute value seen by the load of the boost converter. So on the outside of the load, we're going to see a overshoot at first, but then eventually we're going to get to 500 volts, which is what we wanted to go to that line-to-line 3-phase DC to AC conversion. And then you can go through that, and you can see this signal, which I thought was really cool because you can actually see the duty cycles if you zoom into it. And there it is. And then the power grid. Let's see. Here's the power going in the grid. You can see the volts is 10 to the 5th power up there in the corner. So just make sure you know what units they are. These are much bigger. It's not 0.5 volts. And then here's your current. And the power grid graph is just a little closer of what we were talking about earlier. That's going to sum up this video. It's already at like 8 minutes, so I think that's pretty good. Thank you.